I'll go ahead and get started here. It's a little bit after noon. So today topic is going to be nonlinear regression. And in terms of the next screen here, yeah. So I want to just spend a minute on linear regression. And then there's several different nonlinear regression methods that I want to talk about. Piecewise regression, splines, polynomial regression, and fractional polynomial regression. And actually, these are all linear functions to model nonlinear relationships, and I'll explain that as we go along. And then finally, I want to end up by actually looking at nonlinear regression, where we model it a little bit differently than we do with the linear functions. So linear regression, as I'm sure everyone probably knows, is the formula that we have here, where we have a continuous and normally distributed, although it doesn't have to be exactly normally distributed, dependent variable. And we're going to model that as a function of any number of independent variables, which we designate here by the x's. And the betas are the regression coefficients. And so the beta sub 0 is the intercept term. Beta sub 1 is the regression coefficient for independent variable number 1, and so on. And so obviously it may be the case where we have a situation where the relationships are not linear, and the linear regression model implies that all of the independent variables are linearly related to the dependent variable. And so we have an example here of looking at cholesterol as a function of age. And so we have our data points, and then we fit our regression line, and then we can draw 95% confidence intervals around the fitted regression line. And as you know, probably, that the 95% confidence interval predicts the best at the mean of the independent variable. As you get to the extremes of the independent variable, you have wider confidence intervals. They don't, in other words, it doesn't predict as well out of the extremes. So that's linear regression, which I'm sure everyone is familiar with. But we may have the situation where we have a relationship that is nonlinear. And if we look at the first graph on the left-hand side there, you can see that if we did a linear model for that, that our regression coefficient would be virtually 0. But of course, that doesn't mean that there isn't a relationship there. It's just that it's a nonlinear relationship. And the same with the bottom left graph, that we have a nonlinear relationship, but if we model that as linear, then we're not going to have a very good representation of the data. And you can see that in the bottom, on the bottom right here, the formula is the linear. If we model these as linear, and at the top here, we're modeling it as a nonlinear function where we have the x variable raised to the second power. On the right-hand side here, we have a plot of y as a function of x, whatever those variables might be. And so we might think that, well, maybe the best way to model this is linear. And actually, this is taken from a published article where they did model it as linear. But in looking at the plot, we might think that, well, maybe the linear is not really the best model here, and maybe we could model it as a nonlinear relationship better than we could with just a linear relationship. And so, as I mentioned in the beginning, the outline, there are a number of ways to do this. And the first one we'll talk about is what's called piecewise regression. And piecewise regression is really quite simple. Basically, we're going to find linear functions and come up with more than one linear relationship. And so, for example, for the data in these graphs, we might model this part of it as linear and then model the rest of it with another linear function. But you can see that the two have a different slope, so they're different regression lines. And of course, or at least one of the important things we would want to know here is where is this change point occur? If our interest is in just comparing the slopes of the two lines, that's easy to do. We can just, compare them and see that they're, different slopes to the two lines. But it may be that our interest is actually in finding where the change point is. But there are methods to do that. We don't just have to guess at it. Okay, the second nonlinear regression method I want to talk about is what we call polynomial regression. And this is, as I mentioned, used to model nonlinear relationships. And so what we mean by the fact that this is a linear model for a nonlinear relationship is that it's linear in the regression parameters. And so you can see in our formula here, just like the one for the linear relationship, except now that the independent variable is raised to an integer power. So we have beta 1 times x, which is the linear part of it. Then we have x squared and x cubed, and we could, put as many of these as we think we need out here. And we could include more than one independent variable. So we would have, x sub 1 squared, x sub 1 cubed, and then x sub 2 squared, x sub 2 cubed, and so on. And so the integer or the polynomial regression is, as I said here, easy to apply, but it may not fit well to the actual data. But it is a really common way of modeling nonlinearity with a linear function. So let me give you just an example here. So here's quality of life measures the mean at each month over a year's period. And so our observed means look like this. So we can see that there's sort of an increasing level of the means as we go further out in time. And so maybe we might think, well, we could model this with a quadratic function. That is, we're going to raise our independent variable here, which is month. And so we might get something like that, where we have a change in the slopes of the line. And we can see that that's maybe a better model, or that is a way to model the nonlinear relationship. And we might think, well, maybe just raising it to more than the second power, maybe we can get a better fit. And in fact, if we raise the independent variable here, the month, to the 10th power, we get a function that looks like this. And so you might say, well, that fits really well, because as you can see, the lines actually almost all the time are hit the actual observed means. But of course, the function itself is not very helpful because it doesn't really model the actual relationship. So it might be that in this case, our quadratic, that is looking at raising month to the second power, is a better fitting model. So the next way of modeling nonlinear functions is what we call splines. And this is sort of similar to the piecewise model that I showed in the beginning, but this is a little bit different. And so in the fact that what we want to do is if we have, say, for example, 3 different what we call knots here, we want to be able to model the whole function, and we want to have the points join more or less continuously. And so our function sort of looks like this, where we have our first regression coefficient is linear, and then our second regression coefficient here is where we have x minus a, the first knot. Then we have another regression coefficient where we have x minus b, the second knot, and then the third knot. And basically what this does is it constrains the function to be joined at the knots. And the overall linearity, as tested by whether the regression coefficients still in the linear regression coefficients are equal to 0. The thing with linear splines is that it might not fit some curved functions or highly curved functions very well. So what we do is then try what's called cubic splines. And the cubic spline is basically set up to make the points where we join at the knot smooth. And so the function here that we minimize is what I've given here. I'm not going to go through this in any detail, but basically this is the residual or the error sum of squares to begin with, and so we want to minimize that. And then lambda is a smoothing parameter that controls the trade-off between smoothness and bias. And then our function that we use for the cubic spline. And this turns out to be fairly complicated because our formula then looks something like this if we have 3 knots, where we're going to have a total of 6, or actually 7 if you count the intercept regression coefficients. But you can see that here that for the points, the x minus a, x minus b, and so on, that we're raising those to the 3rd power. So this is what we might get if we use cubic splines as far as looking at our functions. So it looks pretty smooth, and so we would have in this case probably 2 knots. One looks like it would occur about up here, and then the second one down here. And so if we kind of think of this in terms of like integer polynomials, we would have a cube here, because this would be raised to the 2nd power from here to here, and then it changes direction again. So this would be raised to the 3rd power if we were doing just polynomial regression. So another issue then that raises with cubic splines is that it might not fit as well in the tails. In other words, before the first knot and after the last knot. So now we can do what's called a restricted cubic spline that constrain the function to be linear in the tails. And so now we get an even more complicated model that for the 3-knot example will look like this. And so then in the restricted cubic spline function, what we're trying to do is to get a smoothest line or a function, a smoothest function as possible. Okay, let me go on then to one that can be used actually quite easily, although there's software to do the splines and the cubic and restricted cubic splines. And this is, the next one is what we call fractional polynomial regression. And so in contrast to integer polynomial regression, what we're going to do is we're going to raise the independent variables to a power fraction. And so the advantage of fractional polynomials is that we can use this in almost any regression context, including survival or time to event. And typically what will happen is when we do fractional polynomial regression, we'll get a better fit than with just integer polynomial regression. So I know there's a lot of formulas here, but basically the idea here is that we have a link function, the eta, which is what particular statistical method we want to do, like logistic or the Cox model for survival analysis. And we have a set of independent variables, X, a set of regression coefficients, beta, and then P is the powers. And so the idea here is that the G sub X is raised to a power n, which is the P. That's actually should be a sub J. And then for the next, or for the previous point in X, the J minus 1, it's raised to the P times the log of X. And as I say, I'm not going to go through this in any great detail here, but basically what we're going to have is a model of regression coefficients and powers. And so I want to show an example of this, but one of the questions that is probably going to be asked is, well, how do you find the right model in this case? And so we can do that by looking at the model and then looking at a second model and comparing the maximum likelihoods. And if we have one that's is just as good but is smaller than the larger model, then that's the better fitting model. And so what happens is that however many variables that we have in our equation, analogous to stepwise regression, that some variables might drop from the model. So I want to use an example here that we did some years ago that's actually quite a complicated design, but it's actually really easy to do because the software does it all for you. So this was a retrospective cohort study of patients admitted to a private hospital service. And so the primary independent variable here that was of interest was physician workload, which in the analysis here is referred to as census. So when you see census, that's recording or corresponding to the physician workload. And of course, that can change from day to day. The primary outcome, actually there were a couple of them, but the primary outcome was hospital length of stay. And we use what's called an accelerated failure time model, a log logistic model, and I'll explain that in the next slide. But the variables included age, sex of the patient, race of the patient, index of patient illness severity, months from the start of the study, and then hospital occupancy as covariates. And the key thing here is that we had 44 physicians participating in the study, and they billed for over 20,000 hospitalizations among almost 14,000 patients. So you can see we have a lot of data here, a really, really big data set. But just to show you what, well, that's the next slide, but a couple of analytical considerations here is that, first of all, we're going to have clustered data, that is, patients within physician, because the physician's going to see some of the same patients from day to day. And then the census changes from day to day, as does hospital occupancy. And so when we did our length of stay analysis, we looked at 30-day stays. So we then modeled length of stay with a survival function being admission to discharge. And so our first choice was to try the Cox proportional hazard regression, but that really didn't work very well because the proportional hazards assumption didn't hold for almost every covariate. And so we did what's called accelerated failure time log logistic model. And this is a where Cox's regression is a non-parametric statistic, parametric survival analysis or time to event analysis. We model it with a certain distribution. And so in this case, we used a log logistic model. And we determined this by just testing different models like logistic model and the Cox regression, and using the best information criteria, the CBIDS or the Bayesian information criteria, to determine what model to use. And so here's what the data looks like. Obviously just a part of it, but so we have patient ID, and then we have the days that they're in the hospital. They start at day 0, day 1, then day 1 to 2. And so the thing here is that you can see that the physicians see may see more than one patient or different patients. And so, for example, for patient 31 here, you can see that the same physician saw that patient for all 5 days that they were in the hospital. And then we have the census, this is the physician workload. So you can see that that's changing from day to day. The ones that don't change, like age, and this is age divided by 10, so this would be 59. Then we have the patient's sex, the race, the severity of their illness, which I forget what that scale, but I'm probably the higher the number, the worse the severity. And then discharge, which of course everybody is discharged. And then the hospital occupancy, which is expressed as a proportion. And so if we take, for example, patient 42, here we can see that different physicians saw that particular patient. So here's physician 30 on day 1, physician 43, a different physician on days 2 and 3, and then another entirely different physician on day 4. So you can see that's a fairly complicated data set and design. So we have, that's why we're looking at patients nested within physicians. So here's the setup in Stata, and I use Stata because it's really easy to do this in Stata, but you can do it in R or other software as well. And so we have our time interval here from start to stop, where time 0 is their start. We have the patient visit ID, we need to include that. Our failure, which is discharge, which is equal 1. And so this gives us our information for our analysis here in terms of the ID, the failure event, and then our observation time interval, and then exit on or before. And so failure is our discharge. And so our multivariate fractional polynomial regression equation looks like this. We're going to do survival regression. And so our independent variables are going to be census, or this is physician workload, age, female, non-white, and so on. And then in addition to those independent variables, I included the census by occupancy interaction. And then our distribution is log logistic, and then the VC, the variance that we need to consider is physician. So we're going to cluster by physician in our analysis. So I'm going to just go through 3 tables and then 2 figures here. And the figures are really the one we want to focus on because that's where you really see what's going on. But I want to show how this works and how the fractional polynomial works in applying it to our time to event model here. And so one of the things that you get in the output here is the fitting iterations. And so it goes through each variable. And as you can see, generally the first test is a linear one. So this is where we have one means that it's a linear relationship. And then it goes through its iteration and it tests others, so that it tests 0.5, but then it ends up with 2 different powers here. One is a linear and the second one is a quadratic, and I'll show you how that what that means, how that works out. And so for age, we come up with, again, 2 powers, both raised to the 3rd power. And for total occupancy here, we have, again, 2 raised to the -2 power and to the 0.5 power. And so we go through the rest this way in similar interpretation here. So this indicates the final one, how many powers we have and the degree to which that variable is going to be raised. And so for the interaction term here, we've got 2 and 2. And then you remember that I included female and non-white. Those are dichotomous variables. So they're going to have just 1 degree of freedom and be linear in their inclusion in the formula. And then you get this iterates, so we achieve convergence. And then this is then a summary of the different variables that we have in our equation and the powers that are associated with them. And so for census here, we have cubic powers, same for age 10. And as I mentioned, female and non-white would be linear. And then it turns out that the floor occupancy is actually linear, strictly linear. And then our time in months, we have a linear and a quadratic. And then for the interaction, 2 quadratics. And so in terms of developing the model, this is what the covariates then are going to look like. So remember that we had two powers listed for census. I'll just go through a couple here. So we have census raised to the third power minus 3.74 and so on. And then because we had another one, so we have census raised to the third power times the log of census, and then minus a constant here. And you remember that, or maybe not, but going back to the slide where I looked at the form of the fractional polynomial, this is the second term here is the variable times the log of the variable raised to whatever power. And so for age, which we have the first one, we had two cubic terms for age. So we have age to age 10, which is age divided by 10, raised to the third, and then the third age to the 10 raised to the third times the log of age 10, and so on. And then as far as the interaction term here, there were two, and both were quadratic, so that's what they would look like. So in terms of our model then, what we get is our typical regression output. So you see that we have a large sample size here, almost 109,000 patients. And then so for each variable, independent variable in the model, we have regression coefficients for each of the powers. And so those are listed here. And then you can see that female and non-white, because they're dichotomous, have only one coefficient. So what does this look like then in terms of solving our equation for our survival model? So what this would look like then is our survival function would be 0.798, which that was the regression coefficient for census. I'll go back one slide, 0.7598. And that's times census raised to the third power minus 3.742, which was from our output that we got earlier. And then we have 0.579 times census raised to the third power times the log of census, and then minus this constant, and so on through age, female and non-white. And then we could finish that out, but obviously I don't want to take time to go through everyone, but we have the regression coefficients then times, so for example, for the particular independent variable, so in this case, since female is just a dichotomous, a 0, 1, then it would be 0.0344 times 1 if the patient is female, or times 0 if it's male, and then the same thing with non-white, which is a 0, 1 variable. So when we then get to what we really want to see is a plot of these survival functions. And so because we had a significant interaction between census and occupancy, then the first plot here is a plot of the probability of discharge as a function of the census, or the physician workload. And we've done this for different levels of occupancy. So you can see here, we're getting nonlinear trends depending on the occupancy, but we're also getting different functions depending on occupancy. And so you can see that for less than 75% occupancy, we get what we could probably, if we modeled that, is just a simple polynomial is a cubic function where there being a knot here and a knot down here. On the other hand, the 75 to 85% and greater than 85% have different looking functions. And so those appear to be, you could probably just model this with a if you were doing polynomial regression just with a quadratic where we have a change in slope somewhere around here. Although maybe for this one you could argue there's another change in slope here, but anyway, you can see that this is why we're getting the interaction, because we have different functions for different occupancies. So then our primary outcome that we wanted to look at was length of stay. And so again, we look at census, as this is a function of census by occupancy, since we had a significant interaction there. And so we can see that for the greater than 85, we have basically a U-shaped function where we would have one change in slope here. And so that would be akin to a quadratic function, whereas the other two, less than 75 and 75 to 80, appear to have more of a cubic function because they have basically two change points down here and then up here where it goes down again. So, so obviously, when you plot the survival functions, you get more information, or it's more clearly to see what's going on than just looking at the regression coefficients. But we could do the same thing for like age and so on with the other variables, because they were all significant. But these are just two examples here of looking at census by occupancy. So the conclusions that we came up with is that for occupancy less than 85%, the length of stay increased exponentially with increasing census values, but then decreased with census values greater than 20. And then we looked at the high occupancy. We saw that we had a U-shaped function, which was exponentially increasing with increasing census values. But the point here is that even though this looks really complicated, the software that you use basically does all this for you. So even plotting the graphs. So if you have, or you think you have, a nonlinear relationship between an outcome and covariates, fractional polynomials provides kind of a neat way to find that out. So then the last one I want to talk about is where we actually have nonlinear models, and by that we mean they're nonlinear in the parameters. And so the easiest one here, or one of the real simple ones, is where we have e raised to the minus beta, where beta is regression coefficients and x is a independent variables, or a matrix of independent variables. And so you get this asymptotic function that I'm sure you've all seen that looks like this, where you have a steep increase and then the function kind of more or less levels out. So in this case, you can see now the regression coefficients or the parameters are nonlinear. The E is a nonlinear function here. And I could, this is a real simple example, so we could do a much more complicated then. So here's an example of what a two-parameter Weibull function would look like. Weibull functions are used in survival analysis. It's another parametric survival function, but we have two parameters here rather than just one, theta 1 and theta 2. So you see this would be quite complicated. And usually when you have do nonlinear models, just like the fractional polynomial iterates until you get a difference in solution. And also you typically need to provide starting values for the parameters. And I'll give you an example of this here. So a function that I believe this is from more probably basic sciences, wanted to look at the model of total renal volume with age. And so we use a 4-parameter logistic model. And so our model here is total renal volume as a function of asymptote 1 plus asymptote 2 minus asymptote 1 and so on, and then divided by 1 plus the exponent of b minus age. And so asymptote 1 is the asymptote as age tends to 0, and asymptote 2 is age increasing to infinity. The parameter that we're really interested in here is b, because in our model, we're going to get a smooth curve, but this is the inflection where the curve changes from concave to convex. C is just a scale parameter indicating the variance in the model. And the reason that B is a parameter of instance is the age at which there is a change in rate of increase or decrease in renal volume. And the expectation is that this would occur at puberty. So this is the model. I think this is either S or R syntax here, but I think I did this in S, but this would probably work in R as well. So this is my nonlinear mixed effects models, because I have different patients. There's different patients here. And so this is my model. Some of these is fixed models is one, weights, and then A1 plus A2 or model is a random variable. Then we have ID, which indicates that we're clustered by patient. And then these are my starting values for each of the parameters in the model. And then the subset here, that's the subset of patients that I'm using. So that's, again, it's fairly complicated, but actually fairly easy to do once you understand what the model, what you're trying to get out of the model. And so here's the parameter estimates for A1, A2, the asymptote 1 and 2, and then B and C. And of course, the one that we were interested in here is B. And so that estimate comes out to be 12.3. And so this sort of supports our expectation that the inflection between the inflection of the curve is going to occur at about 12 years of age, or approximately at puberty. So if we plot this, this is what it would look like. The dotted lines are the actual individual patients and their total volume at different ages. You can see that there's some real outliers out here, but our primary model, then our 4-parameter model, looks like this, the solid line, and then the dashed lines are the 95% confidence interval. But then where the changes from concave to convex or convex to concave, in other words, the inflection point occurs here at about 12.3 years of age. So that's an example of I guess you might say, a real nonlinear model where it's nonlinear in the parameters. So in summary then, when you do general or generalized linear models, either linear or logistic regression, the assumption is that the relationship of the covariates to the outcome is linear. And so if that's not the case, then we can do we can model nonlinear relationships, and we talked about linear models for doing this, piecewise splines, polynomial regression, whether it's in an integer or fractional. And as I mentioned, nonlinear, what we mean when we talk about a nonlinear model is that we're talking about the model being nonlinear in the parameters, the beta coefficients. When we do nonlinear modeling, regardless of whether we're using a linear model to describe a nonlinear relationship, we have a trade-off between what we call over-smoothed and over-fitted. And so I want to illustrate this by going back to the figure that we had in the beginning, where we had the means of quality of life over a 1 year period by month. And so our observed here was, again, we're just connecting the means at each month, and we can see that we have this sort of nonlinear looking relationship. So if we model this as linear, then we might get something that looks like this. And so we would term this over-smoothed because it doesn't really accurately describe the relationship or the change in mean over the months. Because if we do a linear, then we're assuming that the rate of change is constant over time. And in this case, it's not. So in this case, we have an over-smoothed function. When we did our model to the raised to the 10th power, then we have an over-fitted model, what we call an over-fitted model. And you can see that our model, as I mentioned earlier, almost either goes exactly through or really close to the observed point. So in that sense, it's really well-fitting, but the problem is it's over-fitted because it's giving us a function that's not really helpful or really be really helpful in modeling it. And so it is likely that our best fitting model is going to be our quadratic model, where it's raised to the 2nd power, and I've obviously smoothed that out, but the idea here where we have a quadratic is that there's one change in the slopes of the line, and so we can see that there's a fairly rapid increase here up to June or July, and then it becomes more or less flat after that. So I want to just encourage you, if you are doing this sort of modeling and you have nonlinear relationships, to think about using a way of actually modeling the nonlinear relationship rather than just assuming that a linear relationship is going to be sufficient. So I want to thank you for your time here. And so if there's any questions, we have a few minutes left for that. If not, if you need to go, I'll stay on for a while for any questions. Okay, you're welcome, Lou.